AP Chemistry, this is the day 85 lesson, second lesson in the kinetics unit. It's on writing the rate law. So what does kinetics deal with in chemistry? Kinetics deals with the rate or speed of a reaction. It also deals with the rate mechanism. That is the series of steps that a reaction must go through to get from reactants to products. Okay, now we're going to solve some problems, or actually calculate some rate laws. So this is called the time-independent rate law, and it has the form rate. Okay, so if you look at this equation, nowhere in here is the variable for time. It's based purely on concentrations, and then the equation itself is going to have some value of x for an exponent, some value of y for an exponent, and some value of k, and that will lead you to the rate. Okay, so I want to be sure you know how to do one of these. I'm going to actually write out the series of steps, and I want you to do that as well. So what we're going to do is we're going to find out how much changing the concentration of NO affects the rate. And then we're going to find out how much changing the concentration of Cl2 affects the rate. So what we want to do, we'll start with NO, so I'll write that over here. Okay. And what you do is find two equations. Okay, so you're going to find two reactions where NO changes, the concentration of NO changes, and the concentration of Cl2 remains the same. So we're going to start with NO. Alright, and two reactions where NO changes are 1 and 2. And Cl2 stays the same in 1 and 2. So those are the two we're going to change. Now, so we want to make a ratio of NOs in each of these two reactions. So we're going to put the bigger number, which is 0.5, on top so we don't end up dealing with a fraction. So that's okay to do. You can put 2 over 1. So we're going to do that. Okay, and that gives us a ratio of 2 when you do that. Now we're going to do the same with the rates of those two reactions, and it has to be done in the same order. 2 has to be on top, 1 has to be on the bottom. So we're going to come over here, and when you do that, you get 4. Okay, so what you then do is you find what exponent do you have to raise 2 by to get 4. So the exponent goes on the concentration number, this one. So you're going to write this, 2 to the x power equals 4, and these will generally be some that you can just do in your head. So 2 raised to the 2 power equals 4, so x equals 2 squared. So I'm going to come back here and I'm going to change this to a 2. Now we go down and we do the same thing for Cl2. And the two reactions where Cl changes are 2 and 3, okay, and NO stays the same. So we're going to use 2 and 3, and again, we're going to put the bigger number on top so we don't end up with a decimal number or fraction. So we're going to put 3 on top. So we're going to do reaction 3 over reaction 2. And now for the rates of those same two reactions. Okay, now we're going to see what power do you raise this to get this. So it's going to be 2 to the y power equals 2. And of course, y is going to equal 1. So we can come back up here and change this to a 1. Of course, you don't have to write the 1, but I'm going to go ahead and do it to emphasize that we did that. Okay, good. So now we have these two. Now we have to come up with k. All right, so what you do is you simply pick one of the equations. It could be any one. You'll get the same answer for k. We're going to pick number 1. So what we're going to do is we're going to plug the rate in, 1.19 for the rate. We're going to plug 0.25 in for the concentration of NO, that's this first one. And plug 1.5 in for the concentration of Cl2, that's this second one. In fact, I really should have written it specific to this reaction. So let me just change that now. There you go, that's the way it should have been written. Okay, so we're going to go ahead and do that. So we'll come down here. Okay, and again, let me just note that I used reaction 1 for this. I could have used any of the other two. So now you have one unknown here. So go ahead, grab your calculator and do the math. So I'm going to come down here. I'm just going to quickly divide both sides by this. I'm off screen. I goofed on that one. So let me say that all again. So we calculated K by just dividing both sides by 0.25 squared over 1.5 or 1.5. 0.25 squared and 1.5. And then you end up with 12.7. Remember, when you do this, it's 1.19 divided by 0.25 squared divided by 1.5. Don't multiply these two together. If you do that, then multiply them together, come up with a single number, and then divide 1.19 over that single number. But if you're going to keep them separate, this divided by this, and this divided by this. So anyway, let me go back to say what I said. The way you get the units of measure is rate is always molar per second. That never changes. Here we have K, and here we have the molarity squared, because that's what this is. It's a molarity for NO squared. Here we have the molarity of Cl2 to the first power. So you say K equals m squared m is going to equal m over s. So m squared m equals m to the third. So what we do is we just divide both sides by m to the third. And this is a little bit messy. So let me just go ahead and rewrite that. So you have m on top and m to the third on the bottom and seconds. So m cancels with one of the m's there. Remember, that's m times m times m. So it makes it m squared. So this m on top goes to a 1 because it canceled out. And one of these m's down here canceled, so it becomes m to squared. And then the s just stays there. And there it is. That's the units of measure. So the final equation, rate equation, is going to be this. Rate equals... Okay, so that's the final equation. So what does this mean? It means you could pick any concentration of NO as long as it's not greater than the initial concentration, and any concentration of Cl2 as long as it's not greater than the initial, and plug them in here and figure out how fast the reaction would be with those concentrations. So understand what this equation means. Okay, we are going to go on, and we'll do another one. Okay, so see if you can do this one on your own. It's done exactly the same way. So the rate law is going to look like this. All right, so we need to figure out X, Y, and K. So let's go ahead and do that. We're going to start with NO again. And which reactions are we going to choose? Well, O stays constant in 1 and 2, and NO changes in 1 and 2. So we're going to go ahead and do that. 2 over 1. Okay, and don't let the scientific notation scare you. You just cancel these out. And it's 5.65 divided by 1.41. That's going to be 4. So it's going to kind of end up looking like the last problem. So we're going to come over here and we're going to write 2. So X equals 2 again. So we're going to come back up here and go ahead and change this. Okay, now same thing for O2. It changes in reactions 2 and 3. Now you got to be careful on this one. It's not an exponent of -2, it's an exponent of -1. So you need to get the exponents the same. So you want to make this one smaller because -2 is smaller than -1. So you're going to make this smaller. That means you need to make this bigger. You need to adjust the decimal. So it's going to be this. So now just put a line through this so you don't get confused by it. Okay, again, the 10 to the -2's can cancel, and you have 11.3 over 5.65. And now you have 2 to the y. 2 raised to the y, rather. This looks very much like the last problem. So 2 to the first power equals 1. All right? So now we're going to write out the entire rate law. And we're going to plug in numbers. And let's go ahead and use let's go ahead and use reaction 2 this time. It really doesn't matter. Alright, so we're going to divide both sides by all of this. And I'm going to go up to the top of the page and finish this problem because I don't have space here. You're always welcome to do that too. Now we need to do the same thing on the other side. These cancel. We have just K on this side. A little off screen here. By the way, once this becomes a math problem, you can go ahead and use parentheses if you'd rather. Okay, so I'm going to divide this by these two, and I'm going to take that up to the top of the page. Okay, and what we get is 7118. Okay, and that's our value of K. So I'm going to take it up to the top. And we're going to have this rate. Okay, and you need to figure out the units of measure. That's why I left space there. And it's going to be the same as the last problem. It's a third order reaction, 2 and 1. And it's going to, you can look at the previous problem, going to be 1 over molar squared seconds. You can just memorize these again, or you can calculate them the way I did on the previous example. Okay? Here we go. Let's do one more. So now you know a little trick you got to watch for. Are these exponents all the same? And yes, they are. They're all the same. So we're going to go ahead and work on this. All right. So we got NO and H2. So we're going to find where NO changes and H2 stays the same. Why are we doing this? We're doing this because you want to see these two are the equations where NO changes 1 and 3 and H2 stays the same. We want to know how the change in NO affects the rate of these two reactions. So we want to hold H2 constant so it doesn't have any effect on changing the rate. Only the change in NO does. Alright, so we're going to choose reaction, start with NO again. Here we go. And it's reaction 3 over reaction 1 because we want to have 0.2 over 0.1. Okay, so reaction 3 over reaction 1 is, and for the rate, okay, and again, you can cancel these out now, okay? And you're going to get the same ratio, and it looks like it's going to be a 4 again. A lot of these problems are kind of looking the same. It's all right. So 2 to the x. Okay, x equals 2. So we're going to go ahead and write that somewhere. I'll write it down here. All right, so that is the equation we're looking to build here. We'll go to H2. Okay, and it changes in reactions 2 and 1, and NO stays the same there. Okay, and the rates here are those two. These can cancel, and this is going to again give us a 2. So y is going to equal 1. There it is right there. All right, now we plug in any of the 3. We'll use number 3 this time. Okay, and we'll do the math on this. And I'm not going to write it all out, but you're going to divide both sides by 0.2 squared and by 0.1, and we'll see what that comes out to be. Okay, and I get 1.23. So I can go ahead and just put that here. And the units we get, again, it's a third order. I gave you 3 very similar reactions. Okay, it's 2 plus 1 is 3. So the rate is going to equal 1.23. And I'll just write this up here above. 1 over m squared s. Calculated the same way we did on the very first problem. Okay, I told you to skip this one. It's doable, and I did it one year with my students and just said it's not worth the trouble. It's just a lot of messy math, and it doesn't teach you anything that the other three didn't teach you, and there's no way they would ever give you something this complicated on the AP. They don't want to turn it into a math test. Okay, let's go down here. Okay, let's explain in the glow sticks in terms of kinetics, minimum of 4 sentences, okay? All right, so I'm going to say it. So as the glow sticks moved from colder to hotter water, warmer water, they became brighter. This is because the increase in temperature increased the internal kinetic energy of the molecules. With increased energy, the more molecules exceeded the activation energy and were able to take the reaction forward, to move the reaction forward, and the reaction produced light. So increasing the temperature, if you look at the rate law, increasing the temperature, the concentrations stay essentially the same. They decrease by a tiny, tiny amount, but not by very much during that small amount of time. What changed was the temperature increased the rate constant, K. That made the rate constant larger, and that made the rate faster in terms of the equation. Okay, so go ahead and listen to that, write that down, put that in your own words, and that takes care of this assignment.